So we did this question, and now today we are going to do two different types of questions on Hess's law, where you have to make the equations. Like, look at this one. In this question, you'll be making reactions also. So read the statements very carefully and make the reactions first. And then you are going to use Hess's law to get your desired equation. And you have to identify which one is the desired equation. The enthalpy of combustion of solid carbon means C solid, carbon solid, to form carbon dioxide means carbon solid is reacting with O2 gas. Combustion, right? Combustion means one of the reactant is O2, giving you CO2 gas. This is how you have to make the equation by reading the question. Here, this line is telling you the equation. Solid carbon form CO2 on combustion. So they are not telling you about O2. That you should know. Delta H1, delta H naught 1 is minus 393.7 kilojoules. And this is enthalpy of formation, isn't it? Formation of CO2 from its elements in their standard form. This is formation enthalpy of CO2. If you go back to the table of formation enthalpies, you can see this value there. Right? Now, let's see the next. The enthalpy of combustion of carbon monoxide to form CO2. Again, combustion. But what is the reactant here? So, what are the reactants in this combustion? Yes? What are the reactants? No, no, in second one. First one I have written. Now you have to read the second one. The enthalpy of this one. The enthalpy of combustion of carbon monoxide to form carbon dioxide. What are the reactants here? CO and CO and O2. Yes, CO and O2. So the reaction is CO reacting with O2, giving you CO2 gas. All these are gases. And delta H naught 2 is minus. This equation is balanced. We have to balance it. And look at the value of delta H naught is given for 1 mole per mole of CO. So means this equation should be for 1 mole of CO. So I should put half here then, and it's balanced. Okay, Sarayu, no problem. Take care. CO plus half O2 giving you CO2. So what is delta H naught 2? Minus 283.3 kilojoules. Are you clear that how I have written these two equations from the language, conversion of language into chemical reactions? Now calculate delta H for this reaction. So this is my desired equation. Desired reaction. What do you want in your desired reaction? 2 carbon solid. So what you should do? Take equation 1, yes, multiplied by 2. So it becomes 2 carbon. So I want this. 2 carbon solid. plus 2O2, giving you 2CO2. This is a gas. This is a gas. So these are the changes I have to do in equation 1. What happens to delta H naught 1? It will get multiplied by 2. Okay. Now, very carefully understand one thing. I'm going to skip O2. I'll not worry about it. Why? Because it is the part of both the equations. Can you see? So don't touch it. What you have to do? You have to pick up unique reactants, unique products, which are the part of only one equation. So I'll skip this. Remember this thing. Don't try to balance it. I'm going to do this one. And it is a part of equation 2, you can see. So what should I do to get this? Skip O2. We are going to skip O2 because it is the part of 2 equations. Work with CO. So what should I do with second equation so that I can get 2CO on the product side? Second equation. Reverse and multiply by 2. Very good, Siri. Let's do it. 2CO2. I'm reversing the equation. Reverse. CO2 is now the product. Giving you 2CO plus O2. Now this is a gas. This is all these are gas. It's a thermochemical equation. What happens to delta H2? Anyone? Delta H2 minus 2 times delta H2. Right? Minus why? Because I have reversed the equation. Then multiplied by 2. Now add these two reactions. Add them. And see whether you are getting the desired equation. So what all are cancelling out? Yes. 2CO2, 2CO2. Cancelled. 1O2. So out of 2, only 1 is left. Write down the what is left. The left is 2 carbon solid plus O2 gas, giving you 2CO gas. And that's the desired equation. Yes, good. Can you change your name, Sushant? So he's saying that why, anyone can answer his question? He's saying that why this oxygen should be ignored. I explained it twice. Yes, anyone remember that? Why I'm ignoring this oxygen? I said, don't try to balance this O2 first. Remember I told you? Yeah, because it is present in both the equations. It is present in both the equations, and if I try to do some changes, then I have to do the changes in both the equations, which is very difficult to adjust. So just ignore it. You can see that it balanced on its own. We need not to worry about oxygen. And what is delta H naught reaction? It's the sum of these two. 2 times delta H1 naught minus 2 times delta H2 naught. Plug in these values and you will get the answer. I think Shri is already answering the question. Is it right? She is giving us 220.8 kilojoules. Yes, Dhruv. Good. Good, Shri. Very good. So that's the story about this question. When they will give you question in the form of language and you have to make the reactions, which you see is not difficult. Okay, now let's see one more question. Can I go on the next question now? Okay, I'm going on the next question now. Start reading next question. I'm going to erase this. Okay. Yes. Something similar to what we did just now. You have to make the equations. See, combustion reactions involve reacting a substance with oxygen. Do you know the formula of oxygen? When they write oxygen, please don't take O. What is it? O2. O does not exist. They are not saying here oxygen gas, they are just saying oxygen. It's understood. It's O2. If they say hydrogen, H2. If they say nitrogen, N2. Because they don't exist in OOH. Now, Shrihan has started making the equations. He has read the question. Enthalpies of combustion of C4H4. So first reaction is C4H4 undergoing combustion to give CO2 and H2O. But Shriyan, we have to balance the equation. Balance it. Balance it for 1 mole of this. So 4 carbons, so put 4 here. 4 hydrogens, so put 2 here. 5 O2. This is per mole of C4H4, so it should remain 1 mole. Now let's take the second compound. Is the enthalpy of combustion given to us? Delta H naught 1 is minus 2341 kilojoules per mole, right? C4H8. Let's do that. C4H8. Second reactant. What should I write here? Second reactant. O2. It's a hydrocarbon. Hydrocarbon means hydrogen and carbon only. All hydrocarbons, they undergo combustion to give CO2 and H2O. Balance the equation, children. This also must be for 1 mole of this compound. It should remain 1 mole. So there are 4 carbons, put 4 here. 8 hydrogens, put 4 here. And now check your oxygens. 6O2. This is delta H naught 2, which is minus 2755 kilojoules per mole. All of you are with me? You have written these two equations? This is the desired equation, this one. But there is one more equation given. What is the third equation given? I want you to give me the equation now. There is third equation given. Read carefully. Yes, what is it? Third equation. Yes, very good, Dhruv. But again, this should be for 1 mole, Dhruv. 1 mole of hydrogen. Let's do it for 1 mole of hydrogen. H2 plus half O2 giving you H2O. Right? This is a gas. This is a gas. These are liquids. Gas. Gas. Thermochemical equation. Thermochemical equation means you have to show the states of the matter. Give me 1 second. And what is delta H naught 3? It is minus 286 kilojoules per mole for hydrogen, right? Okay, now you have to use these three equations to get the desired equation. Ready? Who is giving you this? Yes, I want this. Which equation should I take so that I can get this on the reactant side? Which equation? Answer it. Nasya? Yes. Sanjana, Saranya, you're not answering. Equation 1. Take it as such. So I'm writing it. I'm taking equation 1 as such because it's going to give me C4H4 gas on the reactant side the way I want in my desired equation. So I'm not going to do any changes for it. Take it as such. 2H2O, delta H naught 1. And which equation is giving you H2? Equation 3. So what should I do? Multiply it by, multiply this equation by, see this coefficient? 2. 2H2 gas. Then this becomes O2 gas. 2H2O. 2 times delta H naught 3. This will get multiplied by 2. Now, which equation is giving me C4H8? Which equation is giving us C4H8? Second, but do I need to do something? I want C4H8 on the product side. So reverse. Reverse your second equation and it will give you your product of the desired equation. So minus delta H2 because you reverse the equation minus. Now you add all of them and see whether you are getting your desired equation. So cancel the things which are on the different size like 4CO2, reactant here, product here. Then you have 4H2O, correct? Then you have 6O2. See, this is 6O2. Now you're left with this C4H4, 2H2, giving you C4H8. That's the desired equation. So C4H4 reacting with 2H2, giving us C4H8. All of them are gases. What is delta H for this reaction? Is, add all these, is delta H naught 1 plus 2 times delta H naught 3 minus delta H naught 2. And that's the answer. Plug in the values. Yes, Dhruv, very good. Perfect. So children, Hess's law is like a game, isn't it? Making equations, they are not going to ask you to make very tough equations. Most of the time, they ask you to make combustion reactions. So I don't think making equation is a difficult thing. So you can make equations, you can do the operations on the equations, you can reverse them, multiply them, and finally add them to get the desired equation. So this concept was Hess's law. Ready for bond enthalpy, children? bond enthalpies. What are we doing? We are calculating delta H of the reactions by different method. Delta H naught reaction. One method we did by using delta H naught formation values. We defined delta H naught formation, then we did questions based on that. Second method we did this Hess's law. This one. Hess's law means multiple equations are given, just adjust them, rearrange them, multiply, reverse, whatever, to get the desired equation. This is second method. Third method is bond enthalpies. We are going to use bond enthalpies values to calculate the delta H of the reactions. For these bond enthalpies, you should know how to draw the Lewis dot structure. Lewis dot structure. So if this question is there in the exam, then if it is a free response question, then they are checking you for two things. One, whether you know how to draw Lewis dot structure, then whether you know how to calculate delta H of reaction if bond enthalpies are given. So very popular question in free response. Ready, children? Okay. So we are going on the third concept, that is bond enthalpies. How to use bond enthalpies to calculate delta H of the reaction. Okay, let's try to understand. So I'm making an energy profile. You know how to draw the energy profile. Here is the reaction. Oh, sorry. Here is the energy. And on this side, progress of reaction. Rxn means reaction. And this is the energy profile. This reaction is exothermic, endothermic. Is exothermic. So reactant is giving you product. So when the reaction is taking place, then the very first thing that energy is needed. You can see this. Needed, going up. What is this energy? This one. It is the energy needed to break the bonds. Energy needed to break chemical bonds. Right? And you reach the, what is this state called as? Yeah, this state, the one with the highest energy, the one which is least stable, it is called as transition state. And in transition state, the one with the highest energy, you can write it as TS, and you can mark it as like this, transition state. It is indicating bond formation and bond breaking. Bond formation and bond breaking. So bond breaking done, then bond starts getting formed also. They are not fully formed, but they are starting to get formed. So when the bonds are forming, bond formation is exothermic, endothermic. Yesterday I told you about this. Bond formation. The blue one is bond breaking, the red one is bond formation. Bond formation means attraction making, right? Bond formation. Attraction making. So it is, no, you're wrong. Is energy released here or energy is needed in bond formation, children? So it's exo. Bond formation means attraction making. Attractions are formed. Attraction making is exo. Stability, attraction, stable. Stable means less energy. Mantra in chemistry. In the periodic trends, unit 2, check the mantra there. When attractions are made, when plus minus are coming closer, then stability is increasing because the system is losing heat. Because attraction means less energy. Less energy means more stable. So whenever attractions are made exothermic process. Write down in your notebook. So bond is attraction. Bond formation is exothermic. And bond breaking is attraction breaking. It's always going to be endothermic. The blue line, endothermic. You're getting it, children? Please don't do error here, right? Bond formation means attraction making. Attraction making is always exothermic. Na plus coming closer to Cl minus. They are coming closer. Exothermic process. Plus minus attraction increasing. But if they are going away from each other, going away, endothermic. Plus, plus, coming closer, exo-endo. Plus, plus, coming closer, exo-endo. Mhm. It is endo because they are repelling. Minus, minus, exo-endo. These are repulsions. Nature doesn't want repulsions. Repulsion means unstable. Endo. Please don't do error in this. Unit 3 was completely based on this rule. Okay, so here bond formation is exothermic, bond breaking is endothermic. And what is delta H of the reaction? Is this difference? This is delta H of the reaction, right? How to calculate it using bond enthalpies? Don't you think that the energy needed to break the bonds and the energy released when new bonds are formed, the difference is delta H? So when energy needed to break the chemical bonds and energy released to make the bonds. If I add all these energies, if I add sum them, because there are so many bonds in reactant, there are so many bonds in product, add all of them, you get delta H of reaction. Delta H of reaction is summation of, there is a plus sign here, endothermic, bond enthalpies, BE, of reactants. Why it is a plus sign? Because it's breaking. Breaking means positive. Minus summation of bond enthalpies of the products. And why this one is negative? Because it is exothermic. See, exothermic, we were discussing that. Exothermic means minus, endothermic means plus. So, bond enthalpies of the products will be with the minus sign because they are getting formed. Bond enthalpies of the reactant will be with the plus sign because you are breaking them. So you add all the energy needed to break the bonds, all the bonds, and you add all the energies released when new bonds are formed. And then put them with their proper sign, plus, minus, and get the answer. Anyone in trouble with this equation? Okay. Going on the question, now I'm going to use this equation. So I try to explain you some books, AP is not doing it, but some books are writing this equation. The one I have written here, their writing is like this. Just for your information, if you're reading a book, so don't get confused. Delta H reaction is summation of bond enthalpies. That's it. They are writing like this. But here you know that summation of bond enthalpies means bond enthalpies, summation of bond enthalpies of the reactant. This is all bond enthalpies, all reactant product, all. This should be plus. And products, these are only the bond enthalpies we are talking about. Reactants breaking, products making. So in short, this equation can be written like this. Then you have to take care. If you are dealing with a reactant, it has to be positive. If you are dealing with a product, it has to be negative. So generally this equation AP people are not using. So they will be more into this one, right? But the meaning of this equation is also same. Only thing you have to take care of sign conventions. And to XO plus minus. Moving on, children. Yeah, this question. This is a question which is already solved. So first thing is that when the question is given to you, you have to draw the Lewis dot structure and identify the bonds. Like H2, we all know, H singly bonded with H. F2, we all know. So they can combine it like this. They can say, okay, draw the Lewis dot structure of the reactant. This is the Lewis dot structure of the fluorine. 2HF, 2 times HF. You're okay with this? Remember, hydrogen, fluorine, they never make a double bond. They're always singly bonded. So that is the reason their Lewis dot structures are the simplest. So I didn't ask any question here. So we know their Lewis dot structures, right? Okay. Now what bonds you are breaking? Of the reactants. So types of bonds broken. So write down column like this. Bond with the bonds which I'm breaking are HHFF. How many HH bonds I'm breaking is a balanced equation. One HH, one FF. How much energy needed? This much. Because this is this bond energy is always kilojoules per mole. So if it is 2, then you have to multiply it by 2. Right now it is 1. So energy is the same needed. This is energy needed. With a positive sign, add them. Add these values. See, they are adding them. HF is formed. This one is formed. How many such bonds are formed? 2. What is the energy for one bond? This much. 2 means multiplied by 2. And then the energy, this is what? Released. Because it is bond formation. Needed minus, because there is a minus here, released. This is delta H of the reaction. Delta H naught reaction. So what equation I have used? Summation of bond enthalpies of the reactants minus summation of bond enthalpies of the products. I use this equation. Is it okay, children? Okay. Ready to do questions now? This was example. just to show you how to work on these type of questions. Okay. Before going on this question, I would like to do one question from my side. Okay. Okay, one question from my side. From my side. Okay, don't worry about this. We'll do it later on. N2 reacting with H2 giving you ammonia. Equation is balanced. Now you have to identify all bond breaking, the bonds which you are breaking. Can you identify what bond you are breaking? What is the Lewis dot structure of N2? Yes, Lewis dot structure of N2. Only then I can pick up from here. So N bonded to N. This is how the exam paper will be. There is a triple bond, yes. And lone pairs. Now you will go the table. Values of the bond enthalpies will be given to you. 941. How many triple bonds you are breaking? Only one. So 1 times N triple bond N, correct? And the value is 941 kilojoules. H2, H never. No, I didn't get your question. This is for 1 mole. I think units are not mentioned here, but these values are for 1 mole. Kilojoules per mole. This value, oh, okay, I think he's asking that this value is for all 3 bonds. Yes, it will break all 3. All 3 bonds, if you want to break all 3 bonds, then 941, right? It is sp hybridized. Please do not compare its enthalpy with the n single bond n. Somewhere n single bond n is given. Can you see it is not 3 times of this? 3 times of this is not this. Things are different here. Orbital size is different. This is sp3 nitrogen atoms. This is sp nitrogen atom, sp. Hybridization, they are very small. This is the strongest bond if you see. N triple bond N. Is there any other stronger bond? Yes. CO is there. But it is one of the strongest. Can I say second strongest after CO? Because nitrogen are very small atoms, very short, strong, multiple bond. Shorter bonds are stronger bonds. All these things we did. Okay. So that was his question, Shrihan's question. Now there are 3 HH bonds, right? 3 HH bonds which I'm breaking. 3 times H singly bonded H because hydrogen never makes a double or triple bond. So it is 3 times 432 kilojoules because this is for 1 mole and here I'm breaking 3 moles. So these are the bonds I'm breaking. Now add these values. Summation of bond enthalpies of the reactant. How much? Can you add this? Use your calculator, please. Lasya? Ashita, can we answer this? Summation of bond enthalpies. Yeah, please add this in your calculator. Give me the answer. Add these values. Summation means I'm going to add. That's why I'm asking you to add. Work step by step with me. 2237. Thank you very much. 2237 kilojoules. That's bond breaking of the reactants. Good. Now let's do bond formation. Bond formation. So draw the Lewis dot structure of NH3. Ready? Nitrogen, the central atom, skeleton, 3 hydrogens. Hydrogen never makes a double bond. Total valence electrons, nitrogen has 5, hydrogen has 1, 3 times 1, total 8. How many you have used? 6. How many are left out of 8? 6 are used. 2, where it will go on the nitrogen. That's the Lewis dot structure of NH3. How many groups on nitrogen? How many groups on nitrogen? 1, 2, 3, 4. EPA, tetrahedral, molecular geometry, pyramidal, trigonal pyramidal, because one bond is missing. You remember these things? Is it polar or non-polar? It is polar. Watch the videos. We did plenty of examples. It is polar, right? So, how many bonds you are breaking in NH3? How many bonds are forming? Sorry, it's a product. So, how many bonds are formed? What are the bonds which are formed? NH, these. In one NH3, 3 NH bonds in one molecule. And in 2 molecules, 6. So, can I say bond formation is 6 times NH? Pick up the value. 6 times 391. These are the only bonds formed. So what is the summation of bond enthalpies of the product? How much is this? Mhm. Get the summation. Summation, we have only one type. Is it 2, 3, 4, 6? Yeah, good. Yeah, good. Now delta H of the reaction is summation of bond enthalpies of the reactant minus summation of bond enthalpies of the product. Till now, we were doing products minus reactant every time. But now equation is reversed. Now it is reactant minus products. And now you know the reason also. Because you are breaking bonds for the reactant and bonds are formed for the product. This is endothermic. This is exothermic. This has to be plus. This has to be minus. Plug in the values. 2237 energy needed minus 2346 energy released is the delta H of the reaction. How much we are getting? Minus 109. Okay, so delta H, not reaction, is minus 109 kilojoules per mole of nitrogen. Nitrogen 1 mole. 3 moles of hydrogen. So I'm not writing per mole here. I'm writing for this equation in which this energy represents for 1 mole of nitrogen. It also represents for 3 moles of hydrogen and it also represents for 2 moles of ammonia. So I'm just leaving it as kilojoules. Is it okay? So are you comfortable now with this type of question when they give you some question that calculate delta H of the reaction from bond enthalpies? Very popular question. Free response question. So you're going to do like this. You will make 2 columns. See here, I made 2 columns. One, bond breaking. I added all the enthalpies needed to break the bonds. Identify the bond, pick up the values, and add all of them. Here, this one. Then bond formation. Go to the product side, check what bonds are formed. and then add all bond enthalpies. This minus this is the answer. Minus. Minus means exothermic. So this reaction is exothermic. Formation of ammonia. Exothermic. Can you erase this? Ready for this question? Okay. Bond breaking. Look at this and tell me what bonds you are breaking. These are the reactants. So what bonds you are breaking? Identify all bonds which you are breaking. You are breaking hydrogen, carbon. You are breaking carbon, triple bond, nitrogen. You are breaking 2 times hydrogen, hydrogen. 2, right? Yes. So these are bonds which you are breaking. Pick up their values from the table. Hydrogen, hydrogen is here. 2 times 432. This is in kilojoules. Carbon, hydrogen is here. 413 kilojoules. C triple bond N. Triple bonds are here. Kilojoules, right? Now add all these. This is the summation of bond enthalpies of the reactants. This is the energy needed to break all the bonds of the reactant. How much is this, children? How much is this? Bond breaking is from the reactant side. To start the reaction, to make the product, I have to break the bonds. And that is endothermic. So this answer is plus 2192 kilojoules. Very good, Dhruv. Now let's see from bond formation. Bond formation. What are the bonds which are forming? So I'm making 2 columns, right? So this is how you're going to do in your exam, free response. Identify bond breaking, bond formation, show them. Make the Lewis dot structure, show them that you are breaking these bonds the way I'm writing. Okay, 2168. Okay, everybody is saying 2168, so I'm changing this number. Just addition. 2168. Now let's work for bond formation. So what are the bonds which are formed here? How many carbon hydrogen bonds? 1, 2, 3. 3 carbon hydrogen, right? How many nitrogen hydrogen? 1, 2. 2 nitrogen hydrogen. One more. And I think somebody is mentioning Sanjana. Sanjana or Saranya? Saranya. Yeah. She is saying, take this also. This is also formed. Now pick up the values from the table. Carbon hydrogen bonds, same. 3 times 413. 2 times nitrogen hydrogen is 391. 2 times 391. Carbon nitrogen is must be here. No, it is here somewhere. Here. These are carbon bonds. It is 1 time 305. Add all these enthalpies. These are the one which are released. This is the summation of bond enthalpies of the products. How much is this? Okay, what Dhruv is saying, children? You did CN calculation for bond breaking wrong. Why? It's a triple bond. And now the bond formed is single. Values are different. Triple bond is 891. Single bond is 305. Dhruv, was this the question? Okay. No, no. You must ask all the questions. Questions are most welcome. That clears your thinking. Yeah, why not? Carbon can make, you remember carbon has four valence electrons, and I told you in Lewis dot structure, it can make four single bonds with other atoms. It can make a double bond and two single bonds with other atoms. It can make a triple bond and a single bond with other atoms. See here, it's making triple bond with itself. It's making a triple bond with oxygen. It's making a triple bond with nitrogen. Carbon is very popular for triple bonds. Very versatile, yeah. That's why carbon is very abundant. It is the one which can make maximum bonds. Four bonds is like and stable. Of course, it's not the one which can make maximum. If you remember, sulfur can make, it has six valence electrons. It can make six bonds. But making six bonds is difficult task. It can make the molecule unstable. Carbon compounds are very stable. They are very abundant. You have a big organic chemistry on carbon. Okay, can you add these bond enthalpies? People are giving me answer. What was the answer? 2326. 2326 kilojoules. Perfect. So what's the delta H of the reaction? Yes. So this has to be taken plus 2168. It was 8, yes. Minus, this is minus summation of bond enthalpies of the reactant minus of the product because products are formed. This reaction is also exothermic. Yes, bond enthalpies you are not going to memorize. Bond enthalpies will be given to you. Is it 158? Yes. Everybody is saying 100 plus or minus? It's minus, right? Okay, good. That's the answer. It's exothermic reaction. Okay. Now, another important concept before we move on from bond enthalpies to the next topic, that these bond enthalpies which are mentioned here, these are the average bond enthalpies. Average bond enthalpies. What does it mean? Like, for example, carbon. You were saying carbon is very versatile because carbon can make multiple bonds with anyone. So, carbon, when it's making a triple bond with, let's say, another carbon, and then it's making a single bond with hydrogen. This molecule, very popular. So, this carbon hydrogen bond, and if I take this one, try to understand this clearly. This carbon hydrogen bond, and if I take another one, this one, this carbon hydrogen bond, you can see that they should be different. They are not identical. This carbon is sp. This carbon is sp2. Hybridization we did in unit 3, unit 2 in fact, not 3. Review it. And this carbon is sp3. sp carbons, their orbitals are small. All these things we did earlier. So I'm just giving you a very review here. This is sp, mixing of one s with one p, small orbital. sp2 is slightly bigger. This is sp2. sp, sp2. And sp3 is more bigger. So naturally, when big orbitals are there, this line I have already given you. Big orbitals, when big orbitals are participating, that gives you big bond lengths, big bonds. Bonds are big, bond lengths are big. Big bonds means weak bonds, weak, easy to break. Weak bonds means bond enthalpies, BE, bond enthalpies are less. You need less energy to break the bond, or less energy is released when the bond is formed. This thing I have discussed earlier in unit 2, where we were doing this bond lengths, bond strengths. Okay, so it means all these carbon hydrogen bonds where the carbon has a different nature, they are not identical. This one is the weakest because this sp3 is the biggest. This big orbital will give you big bond length. It should be easy to break. Then this one, then this one. But how come they have given us only one carbon hydrogen type of bond length here, bond strength, bond energy? Because they are giving you average, average of all types of bond enthalpies. This is three types here. I can show you more types. This one. This is another type. I can show you more. Like this one. This is another type. This is another type. So these bond enthalpies, which I mentioned here, these are the average bond enthalpies of all types of bonds. Like for example, average age of the class. So there are so many children with different ages. They may differ by 1 month, 1 day, 1 hour, 1 year. But we are talking about the average age of the class. Same here. The bond enthalpies are different. They are not exactly same. But we have taken the average of all types of bond enthalpies in this table. So I want you to understand this word. Is anyone in trouble with this? Children, if you are in trouble with SP, SP2, SP3, please review Unit 2, hybridization topic. Yes, average because the difference will not be very much. Yes, you're right, Dhruv. If I say the average age of this class is 15 years, I don't think I have anyone of 20 years old here. No one. Even if one is there, that one odd case can be adjusted. So approximations, this is how we can learn only. Otherwise, it will become very difficult to use it. So average bond enthalpies are given, and you cannot expect that this is exactly the same bond enthalpy in this molecule. Maybe slightly up and down. Okay, ready for another question? Last question on bond enthalpies, children. This one. We are not doing average for what? Nitrogen? Who said we are not doing? Did I say that these are not the average bond enthalpies? I said average bond enthalpies. So isn't it for nitrogen? I gave you the example of carbon, Dhruv. But all these are average. All of them. I gave you the example of carbon. Nitrogen also has different types of bonds. It is triply bonded like this. It is singly bonded, like doubly bonded like this. Like this. It can be singly bonded like this. So I'm talking about all the values which are mentioned here, not only for carbon. Carbon was one of the example I took to make you understand that bond enthalpies in different chemical environments are different. But here we have taken the average of all different chemical environment for all elements. Okay, ready for this question now? Can you make the reaction? Can you make the reaction, please? Nitrogen gas, isolated nitrogen gas, reacting with hydrogen gas, isolated, giving you NH3 gas. 3 hydrogen. This is the equation. Is there any bond breaking here? On the reactant side, is there any bond breaking? No bond breaking, right? Okay. So they are saying now what is given? Their enthalpies of formation. So delta H naught formation of nitrogen is given. It's not zero because it's not a stable elemental form. You can see the value? It's not zero. Why it is not zero? Because it is not the stable elemental form. Stable elemental form is N2, not N. H is also given. How much is that? This is also not stable. Stable form is H2. H2 has zero value and ammonia delta H naught formation is given. Is minus 46.1 kilojoules. These are the values given. So can you calculate delta H naught reaction here? Now the equation is changed. It is the summation of delta H naught formation of the products minus summation of delta H naught formation of the reactant, right? Plug in the values. Product is this. So minus 46.1. This equation we did in the yesterday class. So minus 46.1. See, formation is given here. So I've written formations. F means formation. Minus, in the parenthesis, this value, nitrogen, 472.7 plus 3 times 216.0. Can you do it? Sanjana, you are writing no for what? So remember the formation value of nitrogen gas is not zero because it is N gas. If it is N2, it would have been zero. So what's the answer? Minus 1581.7 kilojoules, right? Okay. But what is this? During this reaction, are you breaking any bond? This is also equal to summation of bond enthalpies of the reactant minus summation of bond enthalpies of the product is minus 1581.7 kilojoules. So why all of a sudden I'm on this equation now? Because they're asking me to calculate NH bond energy. That's the question. Now read the question and see what I'm doing. I'm calculating delta H of the reaction, and then I'm trying to calculate the bond enthalpies. This is a bond enthalpy equation. That's why I told you at that time. Which one you are talking about? This one? Dhruv, this one or this one? You are talking about equation 1 or equation 2? Dhruv, answer fast. Which equation you are talking about? I think I told you in this equation, reactants are first, products are second because you are breaking bonds and making bonds. That's why. Minus has to be in front of products. Okay, is it okay now? Okay, okay, good. So, is there any bond breaking happening here? No. So, this value is 0. I'm not breaking any bond. So, 0 minus summation of bond enthalpies of the product is minus 1581.7 kilojoules. You can see that there is no bond breaking. You have taken isolated atoms. Only in this reaction, only bond formation is taking place, right? So get the summation of bond enthalpies of the product is this minus minus will become plus 1581.7 kilojoules. Now tell me how many bonds are formed? Draw the Lewis dot structure. How many bonds are formed? 3. So this summation of bond enthalpies is summation of 3 times nitrogen hydrogen bond. That's the only bond which is formed, right? 3 times. So I can say, I'm writing again. So it is 3 times nitrogen hydrogen bond, which I can say as 3x. I don't know the value. So summation of bond enthalpies of the product is 3x, which is equal to 1581.7 kilojoules. So what is X, children? What is X? 1581.7 divided by 3. How much is this? Yes, you're dividing it by 3, right? How come you're getting this answer? Dhruv. Yes, girls, Lasya, what's the answer here? Yeah, that's the answer. Dhruv, what are you doing? No, 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 no. Calculate, estimate. Question is estimate and then compare. Compare. Yes, you can round it off to 1 decimal place. It's okay. Now check, compare. They're asking us to estimate only. Compare. What's the value in the table? What's the value which you have calculated? This is calculated value. Calculated, tabled value. Tabled. Data table. Compare. Compare means now give the reason why they are different. Why these values are different? Because these are average. These are average bond enthalpies. And this is accurately of this NH bond in ammonia. This is accurate. Accurate. This is average. In different chemical environment, average of all chemical environments. whereas this one is actually in NH3, right? So this question is clear, Sanjana? Saranya? Saranya asked a very good question. And I think Dhruv was also very confused with that only because he was giving me some value maybe from the table. Right, Dhruv? You were doing that? He was trying to multiply it by 3 and giving me that value. No, we are not using this table value. We are calculating it from this data given to us and then comparing it with the table value. Yes, you were doing that. Is the question clear now, children? They have given a question. They have given delta H naught formation values. From delta H formation values, I can calculate delta H of the reaction the way we did yesterday. This equation. I calculated delta H of the reaction, which is this value, right? Now, this is equal to the summation of bond enthalpies of the reactant minus product. It's equal to the same thing. This is also delta H reaction, this one. This equation also represents delta H naught reaction. But reactants are 0 here because I'm not breaking any bond. There's no bond. All isolated gaseous atom, no bond, 0. So it means only bond formation is taking place during this change. So this is the energy released when 3 nitrogen hydrogen bonds are formed. So what's the value of one nitrogen hydrogen bond? I assumed it as 3x. I calculated x. My value is this. I compared this value with the value given in the table and I gave the reason that why are they different. Now the reason is why are they different? Because in the table we have average bond enthalpies. Yes, Shrihan. The value which we have calculated is actually the value in this particular molecule. But the value which is given in the table is average. That is the reason these values are not matching. But they are close. They don't differ by 1,000 factor, right? It's not that this is 391, it's nearly 400, that is 500. It's okay. It's close, right? Okay. That's about bond enthalpies. This is a simple question. You just tell me the Lewis dot structure and what bonds are broken and what bonds are formed. And then from the table, we can pick up the values, plug in the values. So first you tell me in this question, which equation you are going to use. You have done so many equations. So which equation here? Mhm. You are dealing with bond energies. Table is given. So which equation? Summation of bond enthalpies. What should I write here? Of reactants minus summation of bond enthalpies of product. I'm going to use this equation. But the problem is that I have to draw the Lewis dot structure of all molecules to see what bonds are broken, what bonds are formed. H2S. Sulfur, hydrogen never makes a double bond. So you can draw it like this. If you draw it properly, then there are two lone pairs on sulfur. H2S and H2O. Exactly same Lewis dot structure, same family, sulfur, oxygen. Fluorine, single bond. Fluorine never makes a double bond. So these molecules are very simple. SF4, sulfur in the center, fluorine never makes a double bond. So it means 4 single bonds. Sulfur has 6 valence electrons. I have used only 4 in 4 bonds Two are left as lone pairs. This is Lewis dot structure of SF4. HF, hydrogen never makes a double bond. Fluorine never makes a double bond. So these are the simplest Lewis dot structure. You need not to scratch your brain for it. Now, can you tell me what are the bonds broken? Bonds broken. This is the last question we are doing on bond enthalpies and bonds formed. Lewis dot structures are there already. Yes, bonds broken. On the reactant side, yes, what are these? Yes, please look at this. What are the bonds broken? Answer, please. Yeah, HS. How many HS bonds? Two. How many FF bonds? Three. Then you have to pick up the values from here and plug in the values. Tell me the bonds formed. Bonds formed. These are the products. Making Lewis dot structure is very, very important to identify the bonds. If you do error in making Lewis dot structure, your question will be wrong. That is the reason this question is free response question. First, they will ask you to draw the Lewis dot structure, and then they will ask you some question like this. How many bonds formed? Mhm. 4 times SF. 1, 2, 3, 4. This one molecule. How many HF? There are 2. There's one HF bond. So 2 times HF. These are the bonds formed. You have to pick up the values from here. And you will add all the bond enthalpies of the bonds broken, all the bond enthalpies of the bonds formed, and then just subtract summation of this formula, right? So don't lose marks in these type of questions, okay? Because they are very simple, hardly any mathematics. Only understanding and application is there. Nothing complicated. Moving on, children. There's a quiz on bond enthalpies on my website. And if you are trying that quiz, I advise you to just have a review of how to draw Lewis dot structures from Unit 2, right? Ready for next topic, children? So what are we doing? We are calculating delta H naught of the reaction. That's what we are doing. Delta H naught of the reaction by different ways. Delta H naught reaction, we calculated it by using delta H naught formation, by using Hess's law. We practiced many questions on these two. And then today we finish with this bond enthalpies, use of bond enthalpies for calculation of delta H naught formation. All these data table will be given to you. You need not to memorize any value. You see, this type of data table will be given to you. Like bond enthalpies will be given to you, formation values will be given to you, Hess's law, equations, multiple equations will be given to you. So data will be given to you and you have to use it to get the delta H naught reaction. That's the aim. This one. This is from data given to you. Now there are two more ways. That is fourth method, cup calorimeter. Cup calorimeter. Experimental. You're going to perform experiment now, children. Fifth, bomb calorimeter. Bomb calorimeter. These are experimental. So, ready? Cup calorimeter, bomb calorimeter. First, I'll take you on the whiteboard. And first, we are going to review some rules of thermodynamics. The very first rule is zeroth law. So don't worry about zeroth law. If you don't remember zeroth, that's fine. Actually, it is called as thermal equilibrium. Thermal equilibrium. This is first thing we have to understand before we start our cup calorimeter and bomb calorimeter. According to this thermal equilibrium, when two objects, so I'm not giving you any proper definition, I'm just trying to explain you. When two objects are in touch with each other, objects are in touch, or two systems, you can say, are in touch with each other, heat flows, heat flows, we already know this. Heat flows from high temperature to low temperature. Let's say you're holding hand of your friend's hand is very warm and your hand is very cold. What happens? Heat starts flowing from the warm hand to cold hand. This is the law of thermodynamics. Heat always flows from high temperature to low temperature. We are going to use it. High temperature to low temperature. This is the law of universe. Pressure also, from high pressure to low pressure. Wind is always flowing from high pressure to low pressure. Heat is always flowing from high temperature to low temperature. Concentration is always flowing from high concentration to low concentration. These are the laws of nature. To low temperature till both objects, they're in touch, right? Both objects are at the same temperature. Objects are at same temperature. And this state, when both the objects are at the same temperature, this state is called as thermal equilibrium. Systems are in thermal equilibrium. Systems. Two objects means two systems. Systems are in thermal equilibrium when their final temperature is same. Thermal equilibrium means final temperature. Children, this will come in the questions, okay? This concept will come in the question. Final temperature is same. Then we say, okay, now these two systems are in thermal equilibrium. Like, they will give you this type of question. There is a cup, coffee cup, that's your cup calorimeter. We assume that this is insulated. A coffee cup, thermocol, heat cannot go in and out. Heat is not exchanging with the surroundings. In this cup, there is water, H2O. Temperature of the water is 25 degrees Celsius. I'm giving you one part of the question, which you will see soon. Okay, so try to understand these terms. Before I go on the questions, I want you to be very sure that you know this word thermal equilibrium and final temperature. If I put a iron piece, this is an iron piece, at 100 degrees Celsius. See, they are in different temperature. I place it here. This is iron piece, Fe. This is water. So two systems, Fe and water, right? Fe is not reacting with water. So can you tell me how the heat will flow? Who is going to lose heat here? Who is going to lose heat? Iron or water? Iron is at 100 degrees Celsius, water is at 25 degrees Celsius. So how the heat will flow? Heat will flow from iron to water. All of you, I hope you are listening because this is something very big in questions. So heat flows from iron to water. Reason? This is the reason. Heat flows from high temperature to low temperature. That's the reason. That you know very well. You have experienced it in your daily life. You touch any hot object, you can see that how the heat starts flowing very fast in your body until they reach at the same temperature. So once they are here in this, now they have become one kind of system together in touch. So what is the final temperature? Both of them will be at the same final temperature. Final temperature will be same. And that's what they will be asking you to calculate. Calculate final temperature. They have the same final temperature after some time, right? Because heat starts flowing very fast from iron to water, and then it will reach an equilibrium, means the amount of heat flowing from iron to water and amount of heat flowing from water to iron will become same. Heat will be flowing, okay? But because they are at the same temperature, so amount will be same. You understood this word thermal equilibrium, children? All of you? Okay, this is zeroth law. Maybe in physics, people are talking about zeroth law, not in chemistry. But there is then first law of thermodynamics that you should know in chemistry also. First law. Now here, who is losing heat? Iron and water, these are two systems. Which system is losing heat? Iron. So you're going to say heat lost. Heat lost is exothermic or exothermic? Heat lost is exothermic. So put a minus here. Heat lost means heat is released from that system. So minus. Heat lost by iron here is equal to the heat gained by water. This is how you're going to work out the questions on cup calorimeter. I'm going to use these two rules. One is that whatever you're going to put in water, they all are going to be at the same temperature after some time. Thermal equilibrium. And then one is losing, other is gaining. The amount of heat lost by any object, anything, any system is equal to the amount of heat gained by another system, because the first law of universe says, or thermodynamics says, energy is conserved. This we have done earlier also with me. Energy of the universe is constant. Heat cannot be created or destroyed. It can be transformed, it can be transferred from one object to another object, it can be transformed from one form to another form, but it cannot be created or destroyed. Here I'm just transferring from one system to another system. So whatever amount of heat is lost by iron, exactly same amount of heat is gained by water. Remember this zeroth law and first law. And now we are ready to learn cup calorimeter. Ready, children, after doing these two laws? Your cup calorimeter is based on these two laws. Okay. So let's start with cup calorimeter. Before we start with the cup calorimeter, I have to introduce you with one more term. This is cup calorimeter. So we'll discuss this, right? But before that, there is very important concept. We need to work on that. That is specific heat capacity and heat capacity of any substance. Specific heat capacity and heat capacity. So first let's start with specific heat capacity. These are the specific heat capacities which are mentioned for different substances. Just like aluminum has a formula Al, smaller mass is 27 grams per mole. It's unique for aluminum. If I say there is an element with 27 grams per mole, you will say, oh, you are talking about aluminum? It's an identity of aluminum, right? Similarly, the specific heat capacity is the identity of the substance. It's fixed. It's like a fingerprint, like you have your fingerprints, which can help you in identifying you. You have your unique fingerprints. Exactly in the same way, every substance has unique specific heat capacities. Check water. Because the type of bonds there, the type of attraction, the type of electrons bound, there are so many reasons that every substance has its unique specific heat capacity. Now, what is the meaning of specific heat capacity? Very important topic, children. Very strongly tested. Look at the units. It is joules. Joule means heat. Joule is heat per gram, 1 gram per degree Celsius rise in temperature. So by definition, it is the heat needed by any of these substances. Heat needed to raise the temperature of 1 gram of the substance, 1 gram, through 1 degree Celsius. That's the specific heat capacity. Check here. Amount of heat, Q, heat required, needed to raise the temperature of 1 gram of substance by 1 degree Celsius. Children, are you okay with the definition? Because then I'm going to ask question. Don't worry about heat capacity. We'll discuss it after some time. Look at this table. Can you tell me what is the substance which needs very large amount of heat to raise the temperature through 1 degree Celsius? Which substance needs more amount of heat to show you the rise in temperature? Yes, water. If I give you water, 100 grams. Answer these questions. These are very popular questions and very confusing if these things are not going straight in your head. If you're struggling, then you'll see you won't be able to answer this question. And mercury, 100 grams. And aluminum, 100 grams. I have given you these three substances, 100 gram, masses are same. Now I'm supplying 100 joules of energy. 100 joules of energy to all the three substances. Mass is same, amount of heat is same. Can you tell me which substance will show you more rise in temperature? Which substance will become more warmer? Which substance will show you more rise in temperature? Wait. Gold I didn't mention is water, mercury, and aluminum. Their specific heat capacities I have circled here. To all of them, I'm giving 100 joules. So in which case, Which one is going to show you more rise in temperature? I'm not getting answer from all of you. Only Shriyan and Dhruv. Girls, Lasya, Ashita. Yeah, good, good. Shri. Are you? Yeah, okay, Lasya, good. So, are you okay that mercury will show you more rise because it needs only 0.139. If you supply 100 joules, it will show you a rise of 13.9. If it is 1 gram, this is 100 gram. Degree Celsius. If I take only 1 gram, then it's 13.9 degrees Celsius. Here, you're supplying, how much is this? It has to be divided, not multiplied. Sorry. It has to be divided. But it's very clear that more is the specific heat capacity. I show you this mathematics which I did, it should be divided. I multiplied it. Okay, more is the specific heat capacity, less is the rise in temperature. You need more heat to raise the temperature. Less is the specific heat capacity, more is the rise in temperature. So mercury is the one which is going to show you the highest rise in temperature, delta T, is change in temperature. Then aluminum, then water. Are you okay with this? And this arrangement is change in temperature is based on their specific heat capacity. When I have taken the amount, these amounts, and the amount of heat, everything I have taken same. So now the only difference is specific heat capacity, and you are going to work out your answer based on that. This question is okay? Okay. Now, according to the definition of specific heat capacity, which generally we are writing as small c, not this, small c. It is the amount of heat needed to raise the temperature of 1 gram. So mass is there, Q is there, C is there, to raise the temperature. So delta T is there. If I use this equation, this definition, then I can make an equation. Q is the heat needed to raise the temperature. M is the mass given to you, 10 grams, 20 grams, whatever, times specific heat capacity times delta T. You can calculate Q for any substance. Is it okay, children? This equation is clear? MC delta T. So this is the equation which is used to calculate amount of heat in cup calorimeter. By using the specific heat capacities of these substances, which you are going to plug in here, you will see the change in temperature. And if you know the mass of the substance, you multiply all these three, you will get the amount of heat transferred to that substance, given or taken from the substance. Is it okay? Any doubt in this question, in this equation? See how the scientists they make the equation. They make the equation based on the dimensional. I show you. Understanding, of course, dimensional. You can understand with the help of dimensional. Check here. Q is mc delta T. What is the unit of Q? Joules. What is the unit of mass? I'm taking gram. What's the unit of C? Joules per gram per degree Celsius. What's the unit of delta T? Degree Celsius. Degree Celsius, gram, gram cancelled. Joules equals to So this equation is perfect. And we are going to use this equation in cup calorimeter. Okay. Now delta T is the difference in temperature. It is always T final minus T initial, always. So you can work delta T in degree Celsius or Kelvin. It doesn't matter. Like for example, if I say the temperature is in degree Celsius, let's say final temperature is 100 degrees Celsius. Initial temperature was 25 degrees Celsius. Delta T is 75 degrees Celsius, right? 75. But if I change this into Kelvin, then it is 100 plus 273. How much is that? 373 Kelvin. Convert this in Kelvin. 373 Kelvin. Convert this 25 into Kelvin. 298 Kelvin. How much is this? Subtract. You'll get the same answer. So please write down in your notes that whenever we are working with delta T, it doesn't matter which unit I'm taking. I can work in degree Celsius and I can work in Kelvin. Is it okay? I hope you have written this example. Write down this example in your notes. So in cup calorimeter and in bomb calorimeter, when you are working with delta T, then in that case, you can take temperature in degree Celsius or you can take in Kelvin. You will get the same answer. So don't worry about the units here. Heat capacity, I'll explain you once we are going to do the bomb calorimeter. There I'll explain you. Can we do this question? Cools. Cooling. Cooling is exothermic, endothermic. Cooling is exothermic. So I should get my answer negative on its own. M C delta T. M is given 869 grams. C of the iron is 0.44 joules per gram. That will be given to you in the question, right? You need not to memorize. So specific heat capacities will be given to you. And delta T is, what is delta T, children? No, no, no. It is minus 89. Always remember it's a state function. T final minus T initial. It's a state function. Final minus initial. And you can see that your answer will be negative, right? Give me 1 second. Okay, I'm back. So I hope this is clear. Here, this negative positive will trouble you. You should know where I'm going to use negative and where I'm not going to use negative. So in this question, I'm just calculating the amount of heat given off exothermic. My answer is negative, you can see. This is the answer, negative 34,000, right? Okay. So you have to take care of delta T every time. Now let's work with the cup calorimeter. Cup calorimeter is working with thermal equilibrium and with first law of thermodynamics, that heat lost is equal to heat gained. So here in this instrument, in this apparatus, which is very simple, it's a coffee cup. You can see there is a lid. This is called as lid of the cup. It's also insulated. There is a thermometer. This thermometer is going to tell you delta T. which is needed in this equation. Q equals to mc delta T. I needed this delta T. In the coffee cup calorimeter, generally, the solvent, there is a solution here. Generally, the solvent is water. So the reactions which are carried out in water, they can be used in coffee cup calorimeter. You cannot do combustion reactions. You cannot deal with gases only. You cannot use a reaction in which all of them are gases. So generally here in coffee cup calorimeter, you will be working with aqueous chemistry. Aqueous chemistry. And this solvent is the water. So water is the surroundings here in the coffee cup calorimeter. It's always taken as the surroundings. It's the immediate surroundings of the chemical reaction. So chemical reaction is system. So whatever change you are doing, whatever you are adding, the substance which you are adding in this coffee cup calorimeter is getting dissolved in water. Then the water is taken as the surroundings always. Remember this line, okay? And the reaction is taken as the system. Reaction is the part which you are observing. Your aim is to calculate delta H of the reaction, right? And this Q, which we are going to calculate in cup calorimeter, is Q of the water, means surroundings, which is equal to mc delta T, where m is the mass of complete whatever material is there, mass of the solution. C is the specific heat capacity of water because it's solvent, it is more in amount. And specific heat capacity of water, you have seen the table, is very high. Yes. You know, the specific heat capacity of water is the conversion factor also, joules to calories. 1 calorie, calorie is another unit of energy, heat, is 4.18 joules. This is the conversion factor also. So you will use this specific heat capacity of water in cup calorimeter. Mass of the solution, m. Delta T from this thermometer, right? Okay, now here when we are working with this cup calorimeter, let's say I added NaOH and hydrochloric acid. Of course, both of them are in water. Both of them are in water, aqueous. Water in large amount. I am adding these here. A reaction starts and I'm getting NaCl aqueous plus H2O liquid. And when the reaction starts, this reaction is exothermic, heat released. So who is going to gain the heat? Water, immediate surroundings, water. And you can see a rise in temperature. Delta T will rise, will go up, right? This rise in temperature indicates, what does it indicate? That water is gaining heat. Water is gaining heat. Then who is losing heat? Water is the surroundings. So Q of the water is positive, is gaining. But then who is losing? This reaction. So minus means losing, Q reaction. Are we okay with this equation? I'm going to use this equation here. Q water, This time in this reaction, exothermic reaction, water is gaining. So there is a plus sign for water and reaction is losing. There is a minus sign for this. If I can calculate this, I know Q reaction. So Q reaction is, they are of opposite sign. One is plus, other is minus always. If water is gaining, reaction is losing. If reaction is gaining, water is losing. So one is plus, other is minus. System and surroundings. First law of thermodynamics. Heat lost is equal to heat gained. So we are going to use this concept. But if you remember, this Q is always in terms of kilojoules, not per mole. But the aim is not this. Aim is to calculate delta H of the reaction. I want to know delta H of this reaction. I don't want to know Q. I want to know delta H of the reaction. That is kilojoules per mole. So I can calculate it. So I'm introducing you with few equations, children. One equation is this. So we will use this equation in our questions. Q equals to mc delta T. To know the amount of heat gained or lost by water, we'll use this equation. The second, we will use this equation, this one, to know the Q of the reaction. It depends what they are asking. Third equation I'm introducing you here is delta H of the reaction, which is actually Q of the reaction over N. N is moles, the moles which are reacting. So you need to know the moles which are reacting, like moles, how many moles of NaOH and HCl, like this. But this Q of the reaction you cannot calculate. What you can calculate? Q of the water. So you're going to say minus, because they are of different sign. If this is plus, then this has to be minus. So minus Q of the water over N, right? These are the equations. Write on this equation also. So Q of the reaction, delta H of the reaction is always minus Q of the water N. Minus why? Because if this is exothermic, that is endothermic. If this is endothermic, that is exothermic. So they have different sign. If I'm taking this as plus, then it is minus. So I'll take minus here. So write on these three equations. One is this. Question will be based on MC delta T equation. Questions will be based on this first law of thermodynamics, heat lost equal to heat gain. You'll be using it. And then you are going to calculate delta H of the reaction as minus Q water over N, this particular equation. These three equations I'm going to use in this cup calorimeter. Is there any problem with any of the concept? I explained you everything. I explained you this part as first law of thermodynamics, this part. I explained you this equation mc delta T from the definition of specific heat capacity. And then delta H of the reaction is kilojoules per mole. So whatever Q reaction is there, we have to divide it by the number of moles to get the unit of kilojoules per mole. So all equations are well defined. So we have less time, so I would like to do few questions before we leave the class. Ready, children? Can you answer this? This question, this type of question we have already done. So read the question and answer it. Leave this part. Largest amount of energy to raise the temperature of 25 grams of the substance from 15 to 37. So which substance needs largest amount of energy? Only, yeah, Siri, very good. Anyone else? I was speaking a lot, so I'm really worried whether you were listening or not listening. So your answer will confirm whether you heard everything. Very good. Very good. I hope everybody's on have understood this. Okay. Now read the second part. The largest temperature change. Who will show you the largest temperature change? Means more rise in temperature when this much amount of heat is given. The largest temperature change will be shown by gold. Yes. You know, children, Indian women, they wear gold bangles. It's traditional here in India. So now I'm not wearing, but earlier I used to. So whenever I used to do cooking, my gold bangles, they become very hot. That's why I removed it now. Cooking means when you are working on the kitchen making chapatis, you know, chapatis in India, rotis. So you're continuously on that tawa near heat. The bangles, they used to become very, very hot. Okay, so because it has the lowest specific heat capacity, so it's going to gain more heat. It's going to show you more rise in temperature. So let's write down this line. High specific heat capacity. Then these questions will become very simple. High specific heat capacity needs more energy. First thing. Second, will show less rise in temperature. Rise in temperature. And that is the reason water, which here in the table you can see has the highest, water is worshipped in every religion because of this. Why we worship water? Why this water is taken as we are searching water on other planets? We are not searching oxygen. What we are searching? Water on other planets. Why is it so? The reason is the heat capacity of water is maintaining the temperature of the earth. It doesn't, it's gaining heat during the daytime, but not showing you much rise in temperature. So maintaining the temperature from the sun is gaining so much heat. If you leave one iron piece in the sun for 2 3 hours, you go and touch it, you cannot touch it. There is so much rise in temperature. But if there is a cup of water, you will see the water will not show you so much rise in temperature. That's how we are surviving. If you remove all the water, then the daytime, the temperature will go very, very high, not fit for surviving many animals and plants and microorganisms, not fit then. That is the reason we are given 80%, nearly 78, 75 or 78% of water on the earth to maintain the temperature. During night, when there is no sun, then water is going to release heat. For every 1 degree drop is going to give you more heat. So it's keeping earth warm during night. So this specific heat capacity is playing a very important role. That is the reason if you check any religion, they all worship water. Okay, so this is high specific heat capacity of which is going to do this. And low specific heat capacity. Yes, children, low specific heat capacity means, what does it mean? It means less energy is needed, less energy to show the rise in temperature needed. And second, it is going to show you more rise in temperature. more rise in temperature. Temperature control is less. If the heat capacity is less, temperature control is less. Show more rise in temperature. If you put it in the heat, it will show you more rise in temperature. You cannot touch it like gold bangles. They gain so much heat. They show you so much rise in temperature. You would like to remove them because of so much heat, right? So understand these terms. Okay, children, this is what is the cup calorimeter, but we have just started and I want you to review the session before you come in the next class because in the next class I will be doing only questions, plenty of questions. You can see there's a big list of questions. Okay, so come prepared for the class. Means review everything what we have done. So if you have any question, you can stay back. Otherwise, we'll see you in the next class.